By the mid-1930s, just 5 fundamental particles were known to physicists. These were the electron, the proton and the neutron, which together form the nucleus of an atom and along with electrons form the entire structure of an atom. Then there was photons, which is what light waves are formed from, and the 5th particle had been predicted by Paul Dirac and discovered in cosmic rays by Carl Anderson, and this particle is known as the positron, and it's the antiparticle of the electron. So everything seemed really neat and tidy. The structure of matter and light was understood in terms of fundamental particles, and every particle seemed to have a role in fundamental physics. Then in 1936, in further cosmic ray research, Carl Anderson and Seth Nedermeyer discovered another particle, which was completely unexpected, and this particle is now known as the muon. And the surprise of the physics community was summed up by Isidor Rabi, who said, "Who ordered that?" Now, 80 years on, our understanding of fundamental physics and the structure of matter has progressed a long way, and the Large Hadron Collider collides beams of protons and large numbers of particles are produced in these collisions. But we now know that all these particles can be explained in terms of just a handful of particles, and they are neatly collected together into a table like the particle physics equivalent of the periodic table, and this table is known as the standard model of particle physics. Most of the particles that are produced in the collisions in the Large Hadron Collider are formed of quarks and antiquarks that are held together by the strong force. And these particles are known as hadrons, and that is the origin of the name of the Large Hadron Collider. Hadrons include particles like the protons that are being collided in the Large Hadron Collider. Proton is made of 2 up quarks and 1 down quark. In addition to the hadrons, there are a small collection of other particles known as leptons that don't feel the strong force. But all these fundamental particles are collected together into the standard model table of particles. And the matter particles consist of 3 generations of each of 4 particles. And those 4 particles are 2 quarks and 2 leptons. So in the first generation, in the first column on the left, there's the up quark, the down quark, the electron, and the electron neutrino. The next column is the second generation, and these are like heavier replicas of the particles in the first generation. They consist of the strange quark, the charm quark, the muon, and the muon neutrino. Then in the third generation, there is the bottom quark, the top quark, the tauon, and the tauon neutrino. Muons are just like heavy electrons. They have the same charges and they feel the electromagnetic and weak forces but not the strong force. The muon is 207 times the mass of the electron. And unlike the electron, the muon is unstable. It decays in about 2 microseconds. The muon is much more penetrating through matter than the electron. Because it is more massive, doesn't bend as much in electromagnetic fields, and it essentially just sweeps the electrons aside as it moves through matter. The tauon is heavier again. It's about 3,500 times the mass of the electron, and because it's so massive, it's even more unstable. It decays in about 1/trillionth of a second. So although it would be more penetrating if it survived longer, it doesn't really last long enough to get very far. Muons are continually being created in the atmosphere, and this happens when highly energetic cosmic rays, that are mainly protons, arrive from distant regions of the galaxy where they have been produced in events such as supernovae. And these protons collide with atoms, nitrogen atoms and oxygen atoms in the atmosphere, and this produces a cascade of particles, many of which are muons. It's estimated that about 150 muons pass through every square metre of the Earth's surface every second. So we're continually being bombarded by muons, but they just pass straight through us. And the muons, highly energetic muon, can pass through up to 1 kilometre of solid ground, but they'll travel much further through a less dense medium such as air. And this has enabled physicists from Japan to take images of the innards of a volcano. And what they've been doing is positioning muon detectors developed for particle physics experiments in laboratories such as CERN around the volcano to measure the flux of muons in different directions through the volcano. So over a period of time it's possible to see the magma chamber within the volcano filling up with magma or emptying of magma, and it's therefore possible to predict when an eruption is likely to occur. And this opens up the possibility of evacuating the population living in the vicinity of the volcano so that they are out of the way should an eruption happen. Muons are now being used to investigate the mysteries of the ancient world. It's long been speculated that there might be hidden chambers within the stonework of the Great Pyramid of Khufu in Egypt. We know of 3 chambers that have been named in modern times: the King's Chamber, the Queen's Chamber, and there's also a hidden other chamber that's unfinished underground level. The Japanese physicists have put muon detectors in the Queen's Chamber to measure the flux of muons in various directions through the pyramid. And they seem to have found evidence of a vacancy in the stonework. So there's evidence of another hidden chamber. And this has led to speculation that perhaps this is where the treasure of Khufu was hidden in the pyramid. So far it's not been possible to investigate the chamber any further, but there are plans to produce a mini flying robot that might be able to peer inside to see what's there. So we can look forward to hearing more about the innards of the Great Pyramid in the near future. So I hope you've enjoyed watching this video, and we'll be putting another video online within the next couple of weeks.